Have you ever gazed at the night sky and wondered how satellites manage to orbit the Earth? It's a thought-provoking question, and one that we're going to unravel today. Let's start at the very beginning. What are satellites, and why do we even bother sending them up into space? Well, a satellite is essentially any object that orbits around a planet. Some of them are natural, like the Moon orbiting around Earth, but many are man-made for various purposes such as communication, weather monitoring, and scientific research. These man-made satellites are the ones we're focusing on today. We've launched thousands of these artificial satellites since the mid-20th century, and they're all orbiting our planet right now. They're like silent sentinels in the sky, constantly circling overhead, out of sight, but always there, performing important tasks that help us in our daily lives. Now let's talk about how these satellites orbit the Earth. There are two primary types of orbits that satellites follow: geostationary and polar orbits. Geostationary orbits are fascinating. Picture a satellite in a geostationary orbit like a child on a merry-go-round. The satellite moves at the same speed as the Earth's rotation, making it appear stationary in the sky from our viewpoint on Earth. This type of orbit is particularly useful for communication and weather satellites, which need to maintain a constant position relative to the Earth's surface. On the other hand, we have polar orbits. These satellites fly in a path that takes them over the Earth's poles. As the Earth spins on its axis, the satellite can cover the whole planet, making this type of orbit ideal for mapping and surveillance missions. So there we have it, a brief introduction to satellites and their orbits. It's a complex dance of physics and engineering, with satellites constantly moving and adjusting to stay in their designated paths around our planet. Now that we know what satellites are and their purpose, let's delve deeper into how they manage to orbit the Earth. So, how do satellites manage to stay in orbit without falling back to Earth? A question that might seem a bit puzzling at first, but the answer is actually simpler than you might think. It all comes down to the fundamental forces of nature, particularly gravity. You see, gravity is the force that pulls objects towards each other. It's the reason why we stay grounded on Earth and why the Earth orbits the Sun. Now, when it comes to satellites, gravity plays a crucial role as well. It's the force that constantly pulls them towards Earth, keeping them from flying off into space. But if gravity is always pulling satellites towards Earth, why don't they just fall back down? Well, that's where the concept of speed comes into play. Satellites are launched into space at incredibly high speeds. These speeds are carefully calculated to ensure that as gravity pulls the satellite towards Earth, the satellite is moving fast enough to keep missing it. Think of it like this. Imagine you're throwing a ball. If you throw it gently, it won't go very far before gravity pulls it back down. But if you throw it really hard, it will travel a much longer distance before it eventually falls. Now imagine you could throw the ball so hard that as it falls towards the ground, the curvature of the Earth falls away beneath it. The ball would, in essence, keep falling but never actually hit the ground. That's essentially what's happening with satellites in orbit. It's a delicate balancing act, a dance between the force of gravity pulling the satellite back and the satellite's speed trying to propel it forward. Too slow and the satellite falls back to Earth. Too fast and it might escape Earth's gravitational pull altogether. The right speed, however, and the satellite will happily continue its orbit. So you see, there's no magic involved, no invisible strings holding satellites up. It's all about physics, about understanding the laws of nature and using them to our advantage. It's all about finding the perfect balance, isn't it? Now, let's talk about the first type of satellite orbit, the geostationary orbit. Delving into the world of satellite orbits, we encounter the fascinating geostationary orbit. This orbit is unique because it allows a satellite to remain in a fixed position relative to the surface of the Earth. Picture this, a satellite in geostationary orbit is constantly moving, yet to us it appears to be hanging motionless in the sky. Quite an impressive illusion, isn't it? The secret behind this celestial trick lies in the satellite's speed and altitude. Geostationary satellites orbit at an altitude of approximately 35,000 kilometers above the Earth's equator. At this height, their orbital period aligns perfectly with the Earth's rotation, which is approximately 24 hours. This synchronization means that as the Earth spins on its axis, the satellite orbits at the same speed, creating the effect of a stationary object in the sky. But why are geostationary orbits so important? Well, their unique characteristics make them incredibly useful for certain applications. One of the most significant uses is in communication. Satellites in geostationary orbit can provide consistent signal coverage to a specific area on Earth, making them vital for television broadcasting and telephone networks. Moreover, these orbits play a crucial role in our daily weather forecasts. Weather satellites in geostationary orbit constantly monitor the same region of the Earth, providing real-time data on cloud formation, wind patterns, and other meteorological phenomena. This constant surveillance allows meteorologists to track storms, predict weather changes, and issue timely warnings. In sum, geostationary orbits are a cornerstone of our modern world, enabling seamless communication and accurate weather forecasting. They allow satellites to provide us with a constant, unblinking eye on a specific part of our planet, and that's pretty impressive. So the next time you watch a weather forecast, remember the satellite providing that information is in a geostationary orbit. Next up is the second type of satellite orbit, the polar orbit. Let's dive right into it. Polar orbits, as the name suggests, are orbits that take satellites over the Earth's poles. Unlike geostationary orbits which circle the Earth's equator, polar orbits are nearly perpendicular to the equator. This means the satellite is traveling from the North Pole to the South Pole and back again over and over. Now, you might be wondering, why would satellites choose such a path? Well, the answer lies in the unique advantages that polar orbits offer. First of all, a satellite in a polar orbit can observe the entire planet over time. As the Earth rotates on its axis, different parts of the world come under the path of the satellite. So, give it a full day and a satellite in a polar orbit will have had the opportunity to scan every corner of the Earth. This makes polar orbits particularly useful for mapping and monitoring purposes. Secondly, polar orbits are ideal for studying the Earth's polar regions. These regions are difficult to reach and observe from the ground, but from a polar orbit, satellites can offer us precious data about these remote and extreme environments. That's why a lot of weather and climate satellites, such as those in the NOAA Polar Operational Environmental Satellite series, use polar orbits. Lastly, polar orbits are also useful when it comes to studying the Earth's magnetic field. Since the magnetic poles and geographic poles don't line up perfectly, a polar orbit can provide a comprehensive perspective of the Earth's magnetic field. It's fascinating, isn't it? How the path a satellite takes can greatly influence what we can learn about our own planet. Remember, each orbit, whether it's geostationary or polar, has its own unique set of advantages. Thanks to polar orbits, we're able to monitor the entire Earth, including the elusive polar regions. So, we've covered a lot about satellite orbits. Let's summarize what we've learned. We started by unveiling the mystery behind satellite orbits, didn't we? We learned that these orbits aren't random flight paths, but are, in fact, a delicate balance of forces. The Earth's gravitational pull tries to bring the satellite back down, while its inertia tries to fling it off into space. It's this tug-of-war that keeps satellites in their orbits, a dance choreographed by the laws of physics. We then delved into the science of orbits. We learned that gravity is the invisible string that tethers satellites to the Earth. This force is what keeps them from zipping off into the cosmos. But it's not just about gravity, is it? It's also about speed. A satellite needs to maintain a careful balance of speed to stay in orbit, moving fast enough to resist Earth's gravitational pull, but not so fast that it escapes entirely. Next, we explored geostationary orbits. Remember those? These are the orbits that allow satellites to stay in the same spot relative to the Earth's surface. They're incredibly useful for things like weather monitoring and telecommunications. To achieve this, satellites need to orbit at an altitude of about 35,000 kilometers, and they need to move in the same direction as the Earth's rotation. And let's not forget about polar orbits. These orbits take satellites over the Earth's poles, allowing them to see the entire globe as it spins below. They're particularly useful for Earth observation satellites, which need to keep an eye on our planet's weather patterns and environmental changes. And there you have it, the fascinating science behind how satellites orbit the Earth. The next time you look up at the night sky, you'll know a little more about those distant lights moving across the heavens.